Hello everyone, welcome to this video. In this video we'll be looking at cyclic groups. So first of all we have to see what are cyclic groups. So suppose we have some group, right? This is the group where the set is represented by G and the operation is given to be the multiplication operator. From this group, that means from this set G, we pick up one element which we call by A, right? So we select an element A from it and we denote within angle brackets the element A to represent this set. Now what is this set? This set consists of all the powers of this particular element A. So this would be A to the power 0, A to the power 1, A to the power 2 and so on, and it would also contain the negative powers, so it would be like this, right? So this set we are calling by this angle brackets A. So this is called the subgroup generated by A. Now I'm saying this as a subgroup. Why? Because this set, right, this forms a subgroup of the group G, right? How this is so? Because if you take some element from it, right, you know obviously A would be present in this set which is generated by A. I'll be telling you the notations and the terminology here later on in this video only, right? So for the time being, you see A is present in this set, right, because you have A to the power 1 here, right? So thus this set is not empty. Now we wanted to prove that this is a subgroup of the group G. So for that we'll be using this one step subgroup test. So we take two elements from this set. So first element we are taking the power as n, so A power n, and the second element we are taking the power as m, so A power m, right? Both the elements, they are present in this subset, right? We can take it, there is no issue, because here both n and m, they are integers. Then we can define the product of this element and the inverse of this element. So it would be A to the power n, A to the power m raised to power minus 1. So it would be A to the power n and A to the power minus m, right? So we can add up the powers here by the exponent rule. So it would be A to the power n minus m, and now because n minus m, that is also an integer, so therefore A to the power n minus m is also contained in this set. So therefore, according to one step subgroup test, this forms a subgroup of the group G, right? So this subgroup A, this is known as a cyclic subgroup of G, right? You can see the cycle here. Cyclic means the things would be repeated after a certain interval of time, right? So this is a cyclic because it is some finite group, right? So the group G is a cyclic group where we say if the group G that is equal to this subgroup only, in that case we call the group as a cyclic group, because this was a cyclic subgroup of the group G. If the group G is nothing but equivalent to the group itself, in that case this forms a cyclic subgroup, right? And moreover, A in this case is known as the generator of the group G. And moreover, you should note that a cyclic group that can have many generators, right? So that means it could be generated by more than one elements within this group. Now this group would contain very many elements, so few elements might work as generators and few might not. So we have to check whether the given element that is a generator of the given group, or it could construct whole of the group by taking its power and so on. Moreover, a set of this kind, that means a cyclic subgroup of the group G, this can have only finitely many elements within it. Why? Because after certain time we are saying that it follows a cycle. So after certain elements, it would have the values which are getting repeated to each other, so therefore it forms a complete cycle, right? This is another point. And the last point here is that every cyclic group is abelian in nature. So that means it commutes here all the elements, they commute with all the other elements of this group. How this is so? Suppose we take two elements. The first element is a to the power I and the second element is a to the power j. Both the elements, they are taken from the cyclic subgroup, right? We know the elements of this group, they are the powers of a, so we can take the elements, two such elements, right? So now if we wanted to check that whether a to the power I, a to the power j, is it equal to a to the power j, a to the power I? If yes, then we say the group is abelian because we have considered two arbitrary elements here. If no, then we would say the group is non-abelian, correct? So according to this thing here, we have a to the power I, a to the power j as equal to a to the power I plus j, right? This thing is equal to a to the power j plus I. So this thing is equal to a to the power j into a to the power I. So this is the result. So this is a basic introduction to cyclic group. In the next video, we will be looking at more results based on the cyclic group. Well, that is it for this video. Thank you for watching.